morning, good afternoon, good evening, wherever you are. Hopefully, you're learning deep reinforcement learning in this lecture series of PhDAI 830 at University of Cumberland's. On a decent note, today is Lecture 11 Proximal Policy Optimization or PPO. It's a continuation. PPO is the algorithm that turned reinforcement learning from a research curiosity into production tool. Introduced by OpenAI in 2017, it solved the core instability problem that had prevented policy gradient methods from scaling reliably. The industry example that best captures its impact is ChatGPT. The RLHF fine-tuning pipeline that shaped the behavior of ChatGPT, Claude, and Gemini all use PPO as the score optimizer. A reward model scores how helpful or harmless a response is. The PPO updates the language model's policy to produce higher scoring outputs. The same clipping mechanism that stabilizes robot locomotion training also stabilizes the training of a 175 billion parameter language model. So this lecture is organized around one central problem and its solution. The problem is that basic policy gradient methods are unstable. A single bad gradient step can destroy weeks of training. The solution is So let me repeat myself because this is significantly important. The solution is organized around one central problem and its solution. The problem is that basic policy gradient methods are unstable. A single bad gradient step can destroy weeks of training. The solution is PPO clipped objective, which limits how far each update can move the policy. A concrete frame for the whole lecture is OpenAI 5 and DOTA 2 agent that defeated world champions in 2019. It trained for the equivalent of 45,000 years of gameplay using PPO across 256 GPUs and 128,000 CPU cores. And the only reason that scale was achievable without constant crashes was PPO's stability. Once again, PPO is the proximal policy optimization. Every topic in today's outline is something the OpenAI's 5 team had to get right. So why advanced reinforcement learning? Before PPO, scaling deep reinforcement learning reliably was extremely hard. The algorithms researchers had reinforced, which we discussed in quite detail, vanilla, actor, critic, A3C, all worked in principle but failed unpredictably in practice. A run would train well for hours and then collapse. We can discuss about Google DeepMind's AlphaGo training in 2016 that happened. The Go playing agent, as we discussed earlier, used policy gradient methods, but the team had to babysit training runs carefully, checkpoint frequently, and restart from safe points when divergence occurred. The engineering overhead was enormous. PPO was designed specifically to eliminate that babysitting requirement, to make reinforcement learning training as fire and forget as supervised deep learning. Limitations of basic policy gradient. The three failure modes here: instability, sample inefficiency, and poor scalability, all showed up painfully in real deployment before PPO. The clearest discussion we can have in this scenario on Waymo's early reinforcement learning experiments for autonomous driving, training driving policies in simulation using basic policy gradient methods resulted in agents that learned well for a while, then catastrophically forgot how to handle intersections or merging scenarios after a policy update went too large. The death spiral was real. A bad update produced a policy that drove poorly, that policy generated bad training data, and the next update was even worse. The team had to invest heavily in checkpoint management and manual intervention. Exactly the operational cost PPO was built to eliminate. So I would strongly suggest you to look into the training instability, sample inefficiency, and poor scalability in more depth to understand all these concepts in more detail. The key idea is trust region optimization, the trust region concept. Do not let the new policy stray too far from the old one per update is the theoretical insight that makes PPO work. The original formulation TRPO enforced this with the hard KL divergence constraint but required computing the Fisher information matrix, which is quadratic in the number of parameters. The industry example I can share with you is Google Brain's robotics work circa 2017. Their team tried TRPO for training. TRPO is training region optimization for training robotics arm manipulation policies, but found it's computationally prohibitive at the scale of networks large enough to handle raw image inputs. The Fisher matrix computation alone took longer than collecting the training data. PPO's contribution was achieving the same trust region effect with a simple clip, dropping the compute requirement for by orders of magnitude and making the approach viable for real robot training. So, why trust regions? That's a great question. Data was collected by the old policy. If the new policy is very different, the gradient estimate computed from the data is wrong. The importance weights become invalid. So do not let the new policy stray too far from the old one. This is significantly important, and you must look at Trust Region Policy Optimization 2015, enforce the hard KL divergence constraints. So this is an area where I would strongly suggest you to look into these topics in more depth to understand, like the practical impact here. PPO trains reliably across robotics, game playing, and NLP fine tuning. With the same hyperparameters, it became the default RL algorithm or reinforcement learning at OpenAI and is the backbone of most RLHF systems, including ChatGPT. The policy ratio RT equals the new policy's probability divided by the old policy's probability for the taken action. When RT equals 1, the data is perfectly on policy. When it drifts far from the gradient estimate, is using data from a distribution the current policy no longer matches. Importance weights become invalid and training degrades. The industry example is NVIDIA's Isaac Lab, a large scale robot sim to real platform. When training locomotion policies for humanoid robots, the team observed that without monitoring, RT policies would rapidly drift, such as collected rollouts were effectively off policy within the single update epoch. Logging RT per mini batch and early stopping epochs when it consistently exceeded 1.3 or fell below 0.7 was one of the key engineering additions that made their training stable across diverse robot morphologies. The PPO objective is elegant. It maximizes the advantage weighted policy ratio but clips that ratio to a trust region and combines this with a value function loss and an entropy bonus in a single differentiable expression. The industry example I can share with you here is Anthropic's constitutional AI training pipeline. The reward model scores model outputs on helpfulness and harmlessness, and PPO maximizes that score while it clip term prevents the language model's token probabilities from shifting too rapidly. Without the clip, early experiments showed that language model policies would collapse. The model would find narrow token patterns that maximally satisfied the reward model but destroyed fluency. So I would strongly suggest you to look into the PPO clipped objective. The diagram shows here in this slide 8. It shows the key geometric insight. Inside the trust region around RT equals 1, the gradient is full advantage weighted signal. Outside the trust region, the gradient is 0 and the objective has been flattened and no longer incentivizes further movement. The industry example I can share with you here is DeepMind's Mujoko humanoid locomotion work. Their team visualized the distribution of RT values across mini batches during training and found that without clipping, a small fraction of high advantage transitions moments where the humanoid took a particularly good step would produce RT values of 5 or 10, dominating the gradient and causing the entire policy to overfit to those rare transitions. Clipping at 1.2 meant those outlier transitions still contributed learning signal within the trust region but could not pull the policy to an extreme. Taking the minimum off the clipped and unclipped objectives means PPO always picks the more conservative of two options. It never takes credit for moving the policy further than the data can actually support. Think of it like the speed limiter on a car. You can still accelerate freely within the safe range, but the moment you approach the danger zone, the limiter cuts in and prevents you from going further. DeepMind trained a five-fingered robot hand to solve a Rubik's Cube using exactly this mechanism. Without the pessimistic bound, the policy would aggressively copy the best looking moves from single training batch, then fails badly on anything slightly different. The conservative clipping forced the robot to only commit to finger movements it has seen it had seen work consistently across many attempts, not just one. Generalized advantage estimation, also known as GAE, is a smarter way to measure how good an action was instead of waiting for the full episode to end, which is noisy, or just looking one step ahead, which is short sighted. GAE blends both approaches using parameter lambda. When lambda is close to 1, GAE looks further into the future. When lambda is close to 0, it relies mostly on immediate next step. The standard setting of lambda equals 0.95 gives the agent enough foresight to recognize that a good action now might pay off several steps later without accumulating all the random noise of a complete episode. Boston Dynamics used this when training their spot robot to walk. A value of lambda around 0.95 let the critic reward a stable foot replacement now because it could see the good balance in the next few steps and follow with being overwhelmed by the noise of a full walking cycle. Why PPO works? A complete picture. PPO works because three things happen at the same time and each one fixes a different problem. Clipping keeps updates safe. Running multiple training epochs on the same data makes it more efficient. Using only first order gradients keep it fast enough to run at scale. Remove any one of these and PPO breaks down. Cohere, a company that builds large language models, trusted this directly. Using clipping alone without multiple epochs was too slow. Using multiple epochs without clipping used the model to collapse. Using second order methods like TRPO was too expensive for the model with 50 billion parameters. Only with all these three properties working together did their fine tuning pipeline produce stable, high quality results, which is exactly why PPO became the standard approach across the language model industry. Getting PPO to work in theory is one thing, getting it to work in practice is another. There are many small details that can quietly break training if done wrong. Forgetting to normalize advantages per mini batch, using the wrong target for the value network, or not clipping gradient norms. Stable Baseline 3, one of the most widely used open source reinforcement learning libraries, took over a year of revisions to get their PPO implementation right. They found the subtle bugs caused 10 to 30% performance drops on standard robot control benchmarks, drops that looked like and the algorithm was simply underperforming, not that there was a bug at all. They eventually published a checklist of 13 specific implementation details, which became the go to reference for anyone building PPO from scratch. Now, this slide is very important. PPO training loop. This has 5 steps. This loop has 5 steps that repeat until the agent is good enough, collect rollouts, and from the current policy, compute advantages using GAE, run multiple epochs of mini batch gradient updates on that data. Update the old policy to match the new one, then evaluate. The most important step is number 3, running multiple epochs. This is what separates PPO from simpler methods that throw data away after one update. NVIDIA's Isaac Gym platform runs 4096 robot simulation, 4096 robot simulations at the same time and collects 16 steps from each per iteration, giving 65,000 transitions per round. They then train on that same data for 8 full epochs before collecting new data. This means each time step of simulation produces roughly 8 gradient updates, which is why they can train humanoid walking policies in hours instead of weeks. PPO keeps the policy exploring through an entropy bonus, a term added to the objective that rewards the policy for keeping its action distribution appeared in terms of spreading out. If the policy starts choosing the same action almost every time, the entropy drops and the objective penalizes that. This keeps the agent trying different things even as it improves. Without this, the agent can lock into the first decent strategy it finds and never discover better ones. So this is something that I would suggest you look into in quite detail so you understand the implications of entropy bonus. epsilon greedy versus entropy regularization, and exploration exploitation balance, which we discussed in the past as well. One of the PPO's most useful properties is that it works for both discrete and continuous actions. Using the same training algorithm, only the output layer of the policy network changes. For discrete actions, the network outputs a softmax probability over choices. For continuous actions, it outputs the mean and standard deviations of a Gaussian distribution. Agility Robotics uses both in their digit bipedal robot. The high level controller picks between skills like walking, stepping over obstacles, or picking up objects. A discrete choice, the low level controller then outputs precise joint torques for 20 joints simultaneously. A continuous action, both run on the same PPO training loop with different output heads, which saved the team from maintaining two completely separate systems and made the overall training pipeline much simpler to manage. PPO has three main knobs to tune: the clip parameter, epsilon, the learning rate, and the GAE parameters. The good news is that the default values are given here for you to look into. So I would suggest you to look into the clip parameter, the learning rate and batch size, GAE discount parameters to understand in more depth how these all values help in terms of the algorithm optimization when you are coding, whether it's Adam, Mujoko, or discrete and continuous values when given in terms of the mini batch size of 32 to 256 number of epochs where k is equal to 4. So this is something that comes handy when you are training any of your potential models. So why PPO training is stable? PPO stability comes from three mechanisms working together. First, the clipping makes the gradient go to zero whenever the policy tries to move too far, like a wall that stops bad updates before they happen. Second, normalizing advantages per mini batch keeps the gradient signal on the consistent scale so the optimizer never sees wildly different sized updates. Third is the entropy bonus, prevents the policy from locking into one behavior too early. Cruise's autonomous vehicle simulation team ran PPO for 18 months of continuous training without a single catastrophic crash, the kind of previously required restarting from checkpoint. They logged the gradient norm, KL, divergence, and entropy at every update step. The clipping triggered on only 3% of mini batches. The KL never got out of the hand, and entropy stayed healthy throughout, which is what allowed them to run a continuous training pipeline instead of a start stop cycle. PPO has been used in remarkably wide range of real world problems, from video games to biology to engineering. One of the most striking example is Google's chip design work published in the journal Nature in 2021. A PPO agent learned to place components on a computer chip, deciding where each circuit block, memory unit, and connection port should sit on the silicon surface. Each placement was a continuous 2D action, and the reward came from how well the final chip performed in terms of speed and wire length. The agent trained entirely in simulation and produced chip layouts that matched or beat human expert designers on several Google's TPU chips in a fraction of that time. This showed the PPO is not just for games or robots. It can solve complex engineering optimization problems that people spend weeks on manually. PPO's three main advantages are that it is simpler than TRPO, more stable than vanilla policy gradient, and more flexible than specialized methods like SAC or Rainbow DQN. When Meta AI was building the training pipeline for their Llama 2 language model, they evaluated several reinforcement learning fine tuning methods. They chose PPO because it was the only one that stayed stable with the reward model and the policy were both changing at the same time, a situation where simpler gradient methods kept breaking. The Llama 2 paper specifically names PPO's clipping as the reason for this stability. Other methods either collapsed when the policy drifted too far from the rewards model training distribution or required so much training that they were impractical at the scale of large language model. PPO's biggest weaknesses are that in it is on policy, meaning it cannot reuse old data and that it can struggle when rewards are sparse or the environment requires extremely precise actions. PPO's six core ideas fit together like a system. So PPO is not the theoretically perfect algorithm, but it is the one that actually works reliably when the stakes are real. So go ahead, apply these in your algorithms learning. You're most welcome to use Google Colab to test all these ideas to allow you to understand in more depth how this works. See you in the next lecture.